Howdy, from the previous 3 videos, we have learned that the intensity of the diffracted beam under the two-beam condition can be written in this format. If the excitation error is equal to 0, the effective excitation error is equal to c to the power of -1. C is the extinction distance. Then Ig can be written as a sine square function of the sample thickness t. What we have here is the analytical solution by solving the Howie-Whelan equation. In this video, I'll walk you through the process. If we think about the electron diffraction in a very general form, the total wave function phi t can be written as the summation of the transmitted beam wave function as well as all the diffracted beam wave function. So the phi t is the total wave function. On the right hand side of the equation, chi is the wave vector. Chi naught is the wave vector for the transmitted beam. Chi g1, chi g2, chi g3, etc. These are the wave vectors for the diffracted beams. If we tilt the crystal to the two-beam condition, we have only two components in the above equation. We have only the transmitted beam and one diffracted beam. If we want to calculate how the magnitude of the electron beam changes as a function of the sample thickness or how far the beam travels through the specimen, we can write this down as d phi over dz. For the diffracted beam, it is d phi g over dz, which can be written down as pi I over cg multiplied by phi naught e to the power 2 pi I bracket chi naught minus chi d multiplied by r plus pi I over c naught multiplied by phi g. And this is what we get for d phi naught over dz for the transmitted beam. Here, I want to say a couple more things about the wave vectors. In these two equations, you can see you have chi naught minus chi d, as well as chi d minus chi naught. So what does this mean? So in the first case, chi naught minus chi d, it is the change in the wave vector as phi g, the beam, scatters into phi naught beam. Similarly, the chi d minus chi naught is the change in the wave vector as the phi naught beam scatters into the phi g beam. In these two equations, we also have c naught and c g. C naught is the extinction distance as we have described before. C g corresponds to the scattering through an angle corresponding to a diffraction vector g. Coming back to chi d minus chi naught, or chi naught minus chi d. So in the exponential form, so e to the power 2 pi I chi d minus chi naught dot r can be written as e 2 pi I g plus sg dot r. Since g and r are perpendicular to each other, so g dot r will be equal to 0. We can cross this out. We will have e to the power 2 pi I sg dot r. This can be further simplified as e to the power of 2 pi I s z. Substituting what we had here into the above two equations, we will get this: d phi g over dz is equal to pi I divided by c g phi naught exponential minus 2 pi I sz now plus pi I divided by c naught phi g. Similarly, For the case of d phi naught over dz, you can also express that as a function of sz instead of chi naught minus chi d. These two equations are very important, and there's a name for that. It is called the Howie-Whelan equations. There is something worth pointing out in the Howie-Whelan equations, is that if you look at the change of the magnitude in phi g, it depends on the magnitude of phi naught and phi g. The same thing down here, if you look at the magnitude change of phi naught, it also depends on phi naught and phi g. You can see that phi g and phi naught, they are dynamically coupled. And this gives rise to the dynamical contrast. In this video, I hope you've had a taste of the Howie-Whelan equations. In the next video, I'll show you how we can reformulate and solve the Howie-Whelan equations.